Hi everyone, welcome to a lesson on impulse through collision. The reason I call it impulse through collision is that collisions are something that we covered in the momentum videos. And it basically boils down to, with very little information about the situation in one instant, you can figure out completely the behavior of the situation, of the system I should say, at another instant, including the impulse delivered by one of these objects on the other, because these two objects, as you can see, have collided and stuck together here. So we're going to solve a car crash question. Actually, no, we'll just call them sliding boxes. I don't want to trigger anyone's post-traumatic stress disorder. So we have one box here, 20 kilograms. Another box here, 100 kilograms. This box is moving to the right at a speed of 10 meters per second. And the second box has zero initial velocity. Once they've collided, they stick together, and we have some mystery velocity over here. We also don't know the impulse supplied by one object on the other. We'll figure that out. So first things first, let's figure out the final velocity of these two objects when they're stuck together. Well, since this object is moving to the right is positive, and that's a positive velocity, we expect this object to collide there and stick together. We also expect the net momentum of this system here to be the same as this system here, simply because it's the same system, just looked at a different instant in time. So we have net momentum is equal to mv, since this is the only moving object. Actually, we'll say m1v1 plus m2v2, m2 being 100 and v2 being 0. So that's equal to 20 times 10 plus 100 times 0, which is equal to 200 units for momentum, kilograms, meters per second, because this comes to 0 over here. So this is the only term that matters. Only moving objects contribute to the momentum of a system. So the net momentum here is 200. We expect the same net momentum over here. So net momentum is equal to 200. And in this case, the masses have joined together. So that must be made up of mv, which is equal to 120 times whatever velocity these blocks are moving at. So 120 times v, 200 divided by 120 is equal to that velocity. And 200 divided by 120 comes to, here's the calculator, 200 divided by 120, 2/3. No, 1 2/3. So 1 2/3 meters per second. And since it's positive, it's moving in that direction there. So we've found the velocity of these two masses stuck together. Does it agree with common sense? Well, this object moving towards the mass of 100 kilograms is moving at 10 meters a second. When it hits the object in front, you'd expect it to slow down. It has indeed slowed down. The 100 kilogram mass, which is stationary, you'd expect to speed up. It has indeed sped up. So I like this answer just for the region of numbers it's in. Now the impulse. I should be more specific. I'm asking here, what is the impulse delivered by the 20 kilogram mass on the 100 kilogram mass? Because the 100 kilogram mass has accelerated, therefore it has changed momentum, therefore it must have had an impulse applied to it. So we can say the impulse upon the 100 kilogram mass is equal to the change in momentum of that mass, since it's the only impulse acting on it, which is equal to m times delta v, which is equal to 100 times 1 2/3, which comes to, I think, around about 167 Newton seconds, since impulse is supposed to be in Newton seconds. Now I'll ask, what is the impulse of the 100 kilogram mass on the 20 kilogram mass? Well, that would be equal to the change in momentum of the 200 kilogram mass, which is equal to m times delta v, which is equal to 20, and delta v being 1 2/3 was the final, take away 10, which was the initial, which is equal to 20 times, what's that, 8 1/3? So 20 times 8.333 comes again to 167 Newton seconds. But actually, so that's negative 8 1/3, so negative 167 Newton seconds. And that indicates the impulse applied by the 100 kilogram mass on the 20 kilogram mass was to the left, because we're getting a negative answer. The next question I want to cover is a tennis ball striking a racket. So I'll leave equals delta P. So now we have a very simple racket and a tennis ball moving towards it with a velocity of negative 10 meters per second. And the initial velocity of the tennis racket is 2.5 meters per second. The tennis racket weighs 350 grams. The tennis ball weighs 60 grams. And an instant later in time, the tennis racket now has some mystery velocity, and the tennis ball, which did have a negative velocity, so in that direction, is now moving in the positive direction with a velocity of 15 meters per second. And the masses have not changed. Let's figure out the magnitude of the impulse delivered by the tennis ball on the tennis racket. We can figure that out before we even find the mystery velocity there. So the impulse delivered, watch the wording carefully, by the tennis ball on the racket looks something like that. And the impulse delivered by the racket on the tennis ball is in the other direction. According to Newton's third law, these should be equal and opposite. So let's find the impulse delivered by the racket on the tennis ball. That would be equal to the change in momentum of the ball, which is equal to m delta v, which is equal to, now we won't use grams, we'll use kilograms. So 0.06 kilograms times, and delta v is equal to 15 take away negative 10. So 0.06 times 25. That comes to an impulse of 1.5 Newton seconds. That is the impulse of the racket, though, on the tennis ball. And the impulse I wanted to find was the ball on the racket. Fortunately, they are equal and opposite. So the impulse applied by the racket on the tennis ball was 1.5 Newton seconds, and the impulse therefore applied by the tennis ball on the racket is equal to negative 1.5 Newton seconds. So we've solved part of our question without even finding the final velocity of that tennis racket. And now let's use this answer here to figure out the final velocity of that racket. So the change in momentum of that racket was equal to negative 1.5, because that's the impulse being applied to it. And that must be equal to the mass of the tennis racket multiplied by the change in velocity, and the change in velocity can be written as Vf take away V initial. So the final velocity take away the initial velocity. We know the impulse, we know the mass there, we know the initial velocity, we just don't know the final velocity. So let's get that by itself. Negative 1.5 divided by m is equal to Vf take Vi. So add vi to both sides. The initial velocity plus negative 1.5 over m equals the final velocity. That comes to 2.5 plus negative 1.5 divided by, the mass was 350 grams, so 0.350, and that comes to 2.5 around about negative 1.79 meters per second. So even if you knew nothing about impulse, you could use the net momentum of this one system and the fact that it doesn't change to find that final velocity. But since we were led to find the impulse first, we can use that information to find the final velocity in another way.